In this section, we're going to generate some matrices from the original matrix. First, I want to begin by specifying what the setSeed option does. So R is a great random number generator, but it turns out that if you don't specify a seed value, every time you generate a random set of numbers or a random number, you're going to get a different number because it is random. There is variation in it. So when we set a seed, you can think of them kind of as pseudo-random numbers. They still are random numbers in their generation, but every time you set the seed value to it, you're going to get the same set of random numbers, hence why they're called pseudo-random numbers. So we set our seed to 1, 2, 3. Arbitrary, you can set it to any positive integer value, and it can be as big as you want. And now we're going to generate a 200 observation random sample with replacement for integral values between 1 and 300. We will call this vector x1, and we're going to introduce a new function called the sample function. And in the sample function, we can specify if we want replacement or without replacement. So from 1 to 300, which is our boundaries, we're going to generate 200 observations randomly with replacement. So what is sampling with replacement? Well, when I pull a number from a bag, and you can think of sampling as doing that, you're just pulling a number from a bag. It turns out when you get that number and record it, you're going to put it back in the bag. That's sampling with replacement. And since these draws are independent, that is the concept of a random sample, you can easily pick that draw again in a subsequent drawing or subsequent sampling because you put that observation or that marble, whatever it is, back into the bag. So you take it out, you put it back in after you record the sample. So let's sample that. Actually, let's do it with our seed. So we set the seed value. And our length of x1 is what we want, 200 observations, randomly sampled from our range of 1 to 300. And in x2, we're going to specify 300 observations, this time without a random sample, but straight from 201 to 500. And our length of x2, here we have 300. I'm going to combine our x1 and x2 vectors together with the C function, where I combine x1 and x2 together into a newly created vector x, and our length of x is 500, exactly what we want. We can enter data into a matrix by doing it traditionally, or we can specify a new option. This new option is called byRow equals true. Now the default, which is what R always goes to, is to do this by column. So in order for you to enter data by row, which means from left to right rather than top to bottom, which is how R does it, they fill columns rather than rows. When we specify this byRow equals true statement in our matrix creation, we're saying that we want our matrix to be filled from left to right. So we generate a new matrix called mat3. We want it from our vector, right? X was again a 500 length vector. And this matrix is going to contain 100 rows, 50 columns, and we want to enter our data from our X vector from left to right until we reach the boundaries of our rows and columns. And just so you can see it, here is mat3. Obviously a rather large matrix to all display, but this does have 100 rows, and 50 columns with it. And this is from, or filled by our vector x, which had 500 observations in it. And you might be noticing that, oh, that's a bit interesting. We have 100 times 50, which isn't 500, but actually 5,000. So we have 5,000 elements in this mat3 matrix, obviously a lot greater than our vector, which only contained 500 elements. So how does R still go through with the procedure of creating a matrix then? Well, it turns out that it replicates certain values when necessary. When it runs out of room, it's going to replicate those values again using the original data set that you specified. So even if you put in a vector that's smaller than the total amount of elements in a matrix, R will still compensate for that by reusing that vector in the matrix creation. So our matrix is pretty messy, right? It has no column names, it just has row numbers. Let's say we want to put arbitrary generic column names so that we have a better, just a cleaner view of our matrix as a whole. So we're going to create a column name vector called cols. I'm going to initialize it. And we're going to use a for loop. So a for loop isn't the most efficient thing in R, but it does get the job done. And since we're doing it for this basic procedure, it's perfectly fine. So in this for loop, we have an arbitrary variable I. You can name it whatever you want. I'm just going to call it I because most sources use I. It's just a temporary placeholder variable. So for I in 1 to ncol mat3. Now what does ncol mat3 symbolize? Well, it's going to give us the number of columns in our matrix. And here we have 50. Why don't I type in 50? I want to automate this. The more that I can automate when it comes to coding or programming, the better it is, because now I'm not specifying everything for each new matrix I want to put into it. Now I just say, oh, for the number of columns in the matrix I want, I don't have to put in a number. R is going to retrieve it automatically, and I've just automated this process. So for each iteration I, from 1 to 50, we're going to use a paste function. We have a character string x. We're going to paste each iteration I, and remember, I takes the value of 1, 2, 3, 4, all the way to 50. Integral whole values. So we're going to have a series of x1, x2, x3, all the way to x50 because we have 50 columns. And our only separation is nothing, so we specify that separation as just double quotations with no space between them. And we're going to fill this cols vector that we initialized outside our for loop with these variable names x1, x2, x3, and so forth. So when I run that loop and I view this column afterwards, here I have my column names. So instead of actually, coding, typing out 50 different column names, we used a for loop, very easy, very straightforward right here, to do it for us. And this was through the paste function. It makes it very simple for tasks like this, and it just gives us a frame of reference for what's happening in large data sets, large matrices, when we can actually name our column headers. So how do we change the column names of mat3? Turns out very simple. There's a col names function. Col names the matrix that we want to replace the names with, and here we have our vector of names. So that changed it. Now let's verify in the output. Let's print out the first 5 rows and the first 7 columns just for reference. And here we have it. So now we actually have a frame of reference for our columns in this 100 by 50 size matrix. So we have x1 representing column or vector 1, x2 representing column 2, all the way to column 50, which is represented by x50. So the paste function is a nice way to do redundant tasks, especially within a for loop, to get it done relatively quickly. Using mat3, let's extract the first 20 rows and every other second column from this matrix. We will call this submatrix submat1, and we specify mat3. We want the first 20 rows, so we use 1:20. And we want every other second column, so we can use a sequence function. We start at 2, all the way to however large or however many columns our matrix contains, right? The reason why I don't write 50 is because I want to automate as much as I can, make it generic and extendable to any type of matrix we want. And we're going to iterate by 2. So we have columns 2, 4, 6, 8, 10, all the way to 50, iterating by 2. And when I run that and print that in our output, here we have x2, x4, x6, x8, all the way to x50. So we jump or iterate by 2, And since we were able to label our column names, we can easily see that our sequence for extracting those every other second columns was successful. We talked about the subset function earlier when we were using it inside of the which function to extract row and column positions that met some type of logical criteria. Now we're going to dive in and just touch the surface on what the subset function is doing. So we're going to use our mat3, our matrix 3, and we're going to subset or list elements as being true if they are greater than 450. And we're going to run this for the first 20 rows and the first 20 columns. So I subset that. And in our output, here we have this. And keep in mind, here we have 20 rows. This is one matrix, but because displaying 20 columns is pretty difficult on any computer screen, it just prints it down here in a continuation. So what is the subset function doing? Well, for row 1, column 1, we have a false value. But for row 10, column 1, we have a true value. Now that's interesting. So let's take a look at mat3. Row 10, column 1. Here we have 451. 451 is definitely greater than 450, so it satisfies that condition. And what the subset function does is it puts a true value when it hits that satisfied condition. So all the subset function is doing is returning logical values in place of each element, which allows us to store those true elements. Now we can remove any rows containing observations greater than 50. Here we go again, introducing the which function with the subset function embedded into it. We have, for our entire matrix, any element in our matrix that's greater than 450, we want that to be specified as true. And using the which function, we can get the row and column position from that matrix. And we're going to place that in a matrix called index 3. And just to reiterate, here we have index 3. This is a, wow, quite a big matrix. A 500 by 2 matrix. Now we're going to list the row numbers containing observations greater than 450. So there's a way that we can do this. It's a little bit of it's a convenient way. But we convert our first column of our index 3 matrix, and our first column is representing the row number. These are numeric values. So what we're doing is we're coercing these numeric values to a factor variable. And a factor variable is a categorical variable that is a grouping. And a factor variable has levels associated with it. So I want to see which rows in our matrix contain these true values. And this is what happens. When we specify our first column containing our row numbers as a factor variable. So we have row 10, row 20, row 30, all the way to row 100. So it looks like it increases by 10 each time. And this is telling us that these rows contain true values that verify or meet this condition that our elements are greater than 450. And now let's say that we want to remove these rows containing observations greater than 450. Well, relatively easy. We just use the bracket notation again. mat3, bracket notation. And we put this with the negative sign or the subtraction sign, however you want to call it, in front of our index 3, and we specify the rows we want to remove, and our rows are contained inside of our index 3 matrix, and it's the first column. So we want to remove those rows, and we want to remove all the columns that come with those rows. And we put that in subset 3. Our dimensions of subset 3 are now a 90 by 50 matrix, so we have 90 rows, 50 columns. So we lost 10 columns from our original matrix in this subset. And just so you can see, here's subset 3, what our subset of matrix looks like. We have our columns, x1, x2, x3, all the way to x50, but now we're 10 rows short, We only printed out the first 5 rows, but obviously we lost the 10th row, the 20th row, the 30th row, all the way to the 100th row. That's how we subset a matrix by using the which function, the subset function, so that we can see what the subset function is doing when we call it in. And in our final section, we're going to look at sorting a matrix. So in sorting a matrix, I found it the easiest to coerce a matrix. So coercion just means that we're forcing a matrix to become a data frame. And remember, a matrix is just a collection of vectors that are of the same length and same class. A data frame, on the other hand, is a collection of vectors of the same length, but you can have in that same data frame numeric vectors, character vectors, as opposed to a matrix where you can only have one class type of a collection of vectors. So the way we coerce any object to a data frame is using as.dataframe, and we specify our matrix. We run that. Subset 3 df. This is our data frame. Now we're going to sort the data frame in ascending order by the first followed by the second variable. We're going to coerce it back to a matrix so we have it in its original form. So here I have as.matrix. This is how you coerce something into a matrix. And we use an order statement here to specify which variables we want to order our data frame, and since we're coercing this back to a matrix, our eventual matrix by. So we're ordering this by the first variable. So $x1, this is the column name for the first variable. And we want to do it by the second variable. Again, $x2, this is the variable name for the second variable. And notice that in this data frame, I use bracket notation again. I want to sort the rows by this in ascending order. And I want to keep all the columns as well, so I leave a space after the comma is used to denote rows versus columns. So running this, here we have subset 3 order. Now we're going to print out the first 5 sorted observations and the first 7 columns of our new matrix, sorted matrix. And here in the output, here we see 86, 86, 86, 39, 39. Things are sorted in that order very nicely. So I hope this tutorial was helpful. We covered a lot of great topics in this, pretty extensively. And just to review, we introduced the concept of matrices, what they are, how they operate. We introduced ways of extracting elements based on logical conditions, using the which function, the subset function, generated submatrices from the original matrix, so smaller matrix partitions from a larger or more giant matrix, because let's face it, we sometimes don't need all the data associated with a matrix. We just want data meeting certain conditions, or we just want a smaller piece of the bigger pie. We define what the subset function was, how it operates, what it's doing, and why we use it, because it's an effective way of extracting elements that meet certain conditions. And finally, we concluded with sorting a matrix. And we sorted a matrix by coercing it or converting it to a data frame, and then using the order function on that data frame and coercing it back to a matrix.